So the title of my talk is using pump probe to measure nonlinear elasticity in the Earth. These are my primary collaborators. One of them, at least one of them is here. We just heard from Paul Johnson, Robert Geyer, Gert Spolkelman, and Chris Johnson. And this is kind of a rough outline of my talk today. First, I'm going to go through some definitions just to make sure everything is clear, and then talk about why we should study nonlinearity in the Earth. Then I'm going to show some examples of some previous work and then some examples of my work. And hopefully everything will kind of tie together. I do have a little section at the end that's somewhat related. It's more on seismicity, and if I have time, I'll get to that. I'm not sure that I will, but I have a little bit of extra stuff as well. So I'm just going to define pump probe. That's in my title. Probably a lot of you know what it is, but just in case not everybody does, this is kind of a physics and engineering 101 version of what stress and strain means in the elastic modulus. If you are, can everybody see my my cursor?
You can see it, Andrew.
Okay, so we have this linear part of the stress strain curve, and then after you get to the yield strength, you get some other kinds of behavior, but most of the time we're working in kind of this linear part of it. And in seismology, we're often working in this linear part of it. And under this kind of view of materials, you really only have to make one measurement and you kind of have everything you need to know about it. But in reality, for rocks, this isn't true. And so we have to have a better way to measure the elasticity of rocks, especially if we want to understand kind of the things that we care the most about in rocks. And that has to do with things like material strength, permeability, porosity. Often we care about fluid-solid interactions and damage properties, all these kinds of things in rocks that we really can't model with this simple view of elasticity. So I'm going to give kind of a description of what pump probe is, and then I'm going to get back into, I guess, the physics and the mathematics that goes with it, but just to define it, since that was in the title of my talk. And this is kind of a complicated figure, but basically on the left-hand side, we have a specimen, which is this gray rectangle, vertically oriented rectangle, and that's some sample, a rock or a piece of metal or concrete or something like that. And it's pumped or strained along its axis, vertical in this depiction of it. And as you strain it, you measure the travel time of a high frequency probe wave across it. And so essentially you're measuring the travel time at different strain values. And not only do you get it at different strain values, but also you get some information about strain history. And so if we look on the right-hand side, on the top axis, this gray figure, this is the low frequency strain. And so these are values of the strain over here, where it's being pumped kind of up and down. And all these circles on here represent measurement points. And so the strain is kind of a continuous pump, but in this example, it's only being measured every so many time steps. But at the time steps, we're measuring both the strain and also the travel time, shown here as the change in the elastic modulus. And they also are measuring attenuation here, which I'm not going to talk much about, but that's another measurement you can get out of these experiments. So when you take the top two, the measurement points in strain and elastic modulus, then you can plot them on an axis that has strain on the horizontal axis and the fractional change in modulus on the vertical axis. And what you can see is it's not, if this were linear, of course, this would all be just a horizontal line. The modulus would be insensitive to strain, but that isn't the case in rocks, and that really isn't the case in most materials, especially things like rocks. And so we see this sort of exotic behavior where the response, the modulus, depends not just on the strain, but on the strain history. And so this gives us a rich amount of information about the material properties and what's happening at the internal contacts, like grain boundaries and fractures and things like that. And that's where all the interesting stuff happens in rocks, both in the laboratory and in the subsurface of the earth. So this is the kind of measurements that I'm going to talk about making in the earth, so that we can learn more than just what the seismic velocities are in terms of like a tomography or something like that. So I'm just going to go through some definitions now, and these are different kinds of elasticity. So classical nonlinearity is essentially Hooke's law with some higher order terms. It's related to the anharmonic properties of materials, and it occurs in single crystals and other intact or homogeneous materials. This little graphic on the right-hand side gives sort of a graphical depiction of what an anharmonic material would be. And so that would be that kind of behavior we would see in sort of more homogeneous kinds of materials. So, and then we have hysteretic nonlinearity, which is elastic behavior with memory. It's usually related to the contact properties across some material discontinuity, like a grain boundary or a fracture or a fault, really at any kind of a scale. And so it occurs in damaged, granular, or heterogeneous materials. We also have both fast and slow dynamics. Fast dynamics is the instantaneous dynamical response of a system. And it's related to putting a material into disequilibria or into a new equilibrium state. Or slow dynamics, which is a time-dependent process that's related to material disequilibria in the process of reacquiring equilibrium. So these concepts are primarily derived from physical laws and laboratory experiments. So why should we study this in the earth? Well, I've talked about that a little bit already. We care about faults, fractures, pores, and grain boundaries. They're the source of nonlinear elasticity. We'd like to monitor the earth systems regarding hazard, usually earthquakes. Sometimes it may be some kind of containment to a reservoir. We also care about porosity, permeability, and the solid fluid interactions. These all occur at material discontinuities. So permeability, stress, material failure, these are the things that we care about most in the subsurface. And we want to be able to leverage the laboratory and theoretical work on rocks as we study the earth. But a major obstacle is making the same kinds of measurements in the earth that are done in the laboratory. So I just have these pictures, these cross sections of what rocks look like under a microscope, and you can see the different grains and things like that. You can imagine if you applied some kind of a stress across these materials, there'd be a force change that would be kind of heterogeneous and be easily perturbed. So why are rocks nonlinear? Well, the effective elastic modulus and the velocity of rocks depends on the grain coordination number, the grain contact stiffness, grain contact geometry, which are all affected by the stress state, the porosity, the pore fluids, and the elastic properties of grains. So each possible grain configuration represents a different elastic state with different force chains. And then we can imagine at bigger scales in fault zones and things like that, we have different amounts of damage depending upon the strain and the strain rate and the strain history, where we have usually a fault core that could be anywhere from meters to tens of meters or so. And then you have like a damage zone that can be anywhere from tens to hundreds of meters to maybe even a few kilometers in some cases. So the mathematics of it looks something like this. So this is getting back to the classical nonlinearity, where we have Hooke's law with some extra terms. And so we might have a linear part of the stress strain curve and then some other part that's nonlinear, and that would be represented by these higher order terms. On the left-hand side, we have the beta term, which is the second order coefficient, and then there are different formulations upon it, depending upon which method you look at, the different ways to formulate the higher order terms. And then we have the hysteretic nonlinearity in damaged or heterogeneous materials. And then we have to have another term which has the strain and the strain rate in it. And you'd have a function that looks like this, where strain history is important. And so in this case, during a material that's pumped several times in kind of a complicated way, ends up with all these little internal loops that happen, and that's because the elasticity depends on both the strain and the strain history. And so we have some sort of a path where the seismic velocity may change over time even at the same stress level. So this is just kind of a summary. So we have linear elasticity where the slope is constant between stress and strain. We have the nonlinear classic nonlinearity, which just has Hooke's law with some extra terms. And then we have the hysteresis, which has a dependence on strain rate and also strain history. And these are just some other aspects of traveling waves and things like that. So that's linear, that's nonlinear classic. I couldn't come up with a good graphic for the hysteresis, but that would involve contact behavior on faults and fractures and grain boundaries and things like that. So what is the mechanism for nonlinearity in the Earth? Well, there are different ways, there are different ideas or different models. One is, or a couple of them are this bimodal elastic behavior, where you can model it as a series of springs where the contacts would have a different stiffness, usually softer than the grains themselves would have, sometimes with damping and things like that. There's also contact behavior where you have different kinds of contacts that some of them which would result in either linear or classical nonlinear behavior, and others that would have a state of being opened or closed. So contact behavior, and that would produce the hysteretic behavior. And so we have, these are kind of a summary of some of those things. So we have contact physics, and we have crack healing model, shear STZ, shear transfer zone. So they all have ways of modeling what we observe in the laboratory in terms of both fast and slow dynamics and different kinds of observations. So contact physics model is applicable for consolidated and pre-compressed unconsolidated materials. The model is hysteresis and slow time relaxation and provides a contact scale. Crack healing, you can model consolidated materials with microcracks, models hysteresis and slow time relaxation. And STZs are non-consolidated materials with grain restructuring. And you can model fast time processes, including nonlinear resonance and losses. And also I mentioned fast and slow dynamics, and this is the way I like to think about it, because I'm going to be talking about this a little bit later with some of the observations where you have more than one energy state, which relates to different contact behaviors. And when something is perturbed, it goes into some kind of a metastable state, and it sits there for a while, and it might be softer. And then over time, through some sort of thermodynamic process, it will achieve equilibrium over time. And so you'd have fast dynamics. So you have an instantaneous softening of a material, for example, and then a slow recovery to its original state. And that's related to either dislocations or grain boundary sliding, microfractures, macrofractures, faults. Really could happen at any scale, but probably most likely it's happening at the smaller scales here. And so this is how it would look like in terms of contact behavior, where you have some of these contacts which are behaving more in a linear fashion. And then we have these other contacts in here that would be modeling the hysteretic nonlinearity. So they could open and then they could close into some sort of metastable state, and then over time they would return to their initial state. And so that would be fast and slow dynamics. So I'm going to talk about some examples at the laboratory scale. And what I'm going to be focused on here are these three questions at the top. So does nonlinear behavior evolve in faults through the earthquake cycle? Does nonlinear behavior evolve in subsurface reservoirs while fluids are extracted or injected? And can we measure these changes and understand what they mean? And so what I'm going to show you first is this laboratory example where we have, this is in Chris's lab, where there's this experiment where there's a block in the middle. It's pressed between these two side blocks here. There's this halite in brine, so a granular material with fluids, and measure how that evolves over time with both normal and shear stressing. And so what we see here, first under just normal loading, so this isn't the middle block, normally is going to be driven down the middle, but this is just this part of it is just the normal loading from the sides. And what we can see is that we have both instantaneous response, so fast dynamics, where the porosity jumps down and the velocities jump up, but then there is a time-dependent aspect to it as well. So the porosity goes down immediately, but then it continues to go down over time, and that's mirrored by the velocities Vp, Vs, and the amplitudes as well. And so this is a time-dependent process. And then they continued with shear loading in this experiment. And so there is also both instantaneous and time-dependent processes. So the shear stress, the shear displacement is here. So there's a hold and then a shear displacement and then hold again. And so initially the shear stress goes up, and then it reaches the peak. And this is zoomed in over on the right-hand side. And we can see that there's a peak shear stress, and then there's some kind of a failure, and then the porosity continues to go up even after peak shear stress. So there's some kind of dilation. And that's affecting both the porosity and the velocities. And so these are the kinds of things that we expect would be happening in real fault zones. And so can we understand these processes in the labs and then try to look at in the earth and try to see if we can understand what's happening in the earth. So I just wanted to show one more before I talk about a comparison with what might be happening in the earth. This is rough limestone with no granular material, and this is a little bit different than what we saw with the granular material. We have the shear stress amplitude probe, velocity probe, and dominant frequency probe, similar to what was in the other experiment. And we can see here, for example, that the peak shear stress happens after the peak amplitude and velocity. So this is perhaps some kind of precursory activity that happens before failure. And so these are the kinds of things we're going to be looking at that we'd really like to be doing in the earth. We want to understand what's the current state of a fault, and can we learn anything about precursory activity that might tell us about what's going to be happening in the near future. So now I'm going to talk a little bit about some examples at Earth scale. The first one's an active source experiment, and this one is really cool. This one's really cool. So so in the Earth we have either a natural pump in the form of either earth tides or barometric pressure or something like that, and we have an artificial probe. So these will be active source experiments that have where the probe is the active source, and the pump is some kind of a natural phenomena like solid earth tides or barometric pressure. So here we are at Parkfield. This is at the SAFOD site. For those of you not familiar, there are two boreholes. One of them is called the pilot hole that was drilled first. And then there's the main hole where they drilled right into the fault zone. But in this experiment, they were not right in the fault zone. They had a source and receiver, so they were measuring travel times between these two boreholes. And they were measuring it over some period of time as for example, as there were strains primarily due to barometric pressure. But the other thing they ended up catching was precursory activity for two small earthquakes. And so in this figure right here, this is like a side view. So this red square right here is essentially those two boreholes that we saw on the previous slide. And then these circles down here are earthquakes. And the red circle represents a magnitude 3 earthquake, and the green circle represents a magnitude 1 earthquake. And on the right-hand side, we have creep measured with a nearby creep meter, GPS, stress change, and S wave plus the coda delay. But what's important here is this down here, the estimated time delay in relation to these two earthquakes. So the hypocentral times are denoted by these vertical lines, the red vertical line here and the green vertical line here. And what you can see is that the time delay for the probe wave across the two boreholes started to increase even before the two earthquakes occurred. So this is about a day earlier. So this shows us some kind of precursory activity before this magnitude 3 event, even though the magnitude 3 event was actually a few kilometers deeper than where the measurements were made. And this is also true for the magnitude 1 event, which was closer but smaller. There was also the dilation, or the delay times started even before the earthquake occurred. So what's going on here? Is this the same behavior what we saw in the laboratory? So if we look here, these axes are upside down from one another, but the peak shear stress is the time when the material reaches its maximum strength and starts to slip, which would be at the time of the earthquake over here. And we can see in the laboratory that before that, we had decreases in velocity, and then afterwards we continued to see decreases of velocity even after we reached peak strength. And that's really exactly what we're seeing here. It's a little bit hard to talk about precursory activity here because the system was there's no shear being applied out here, and so that's different than what we see in the Earth. But in terms of the relationship between the peak shear, it looks very similar to what we see in the Earth. And so this gives us some kind of a link between what we see in the laboratory and what we see in the Earth, and also some hope that we can forecast behavior in the Earth by making these kinds of measurements. So this is what kind of an earthquake cycle looks like. So we have this interseismic time on the left side of this axis, where the slip rate is very low and the shear stress is increasing quickly. We get to nucleation, where the slip rate starts to increase and we reach our peak shear stress. And then we have the coseismic part of the cycle, where we're slipping rapidly and the shear stress drops quickly. And then we in the post-seismic, where the slip rate is decreasing, and then we start to accumulate shear stress again. And so we'd like to know where in the cycle we are. And we know that when we're near nucleation, a lot of things are happening. We saw that in the previous slide. But does anything change throughout the rest of the cycle that we can measure? And so in the case of what we saw at the SAFOD site, we saw an increasing shear stress, the dilation and reduced modulus right up here in this part of the cycle just before nucleation. So this is probably far in the future, but these are the kinds of things we know that we can measure in the lab, and we'd like to be able to measure in the Earth. So now I'm going to talk about some other examples at Earth scale, but these are passive source. And so this is a pump probe with a natural probe. So the pump in this case is going to be the solid Earth tides, and the probe is going to be empirical Green's functions. So this is a study in Pinyon Flats in California. There's an array of seismic instruments and using empirical Green's functions to measure changes in travel times over the course of seismic cycles. What we're looking at here is the tidal strains in these three axes, the north, south, east, west, and up, down. And what we can do in this study is measure the difference, create empirical Green's functions from different parts of the cycle and then compare them, and to try to see if there are any velocity differences that are associated with this tidal strain cycle. And what they find in this study, that it's actually faster, dV over V, when during periods of compression. Sorry, it's slower when it's compressed. So it's very similar to what you experience when you're on the beach. So if you've ever been on wet sand, you know that when you step down, the sand around your foot gets dry. And the reason why it does is actually when you compress it, you're actually increasing pore spaces, and then the water gets drawn into those pores and it dries out, at least on the surface. And that's the behavior they observe here in the very shallow subsurface. So we're really talking about in the upper few meters. So when you compress it, you actually increase pore spaces, and that decreases the pore pressure. And that's what we observe. That's what they observe in this study. That's kind of the opposite of what we expect in more consolidated materials, where we expect things to be faster when they're compressed. So this is another study, but with an artificial probe, a natural pump and an artificial probe. And this one is a little bit more relative to the kinds of things that I care about, stress and permeability and things like that in the Earth, and not in the unconsolidated material in the top few meters, tens of meters, but in consolidated material, crystalline material, deeper material. So this is nonlinear behavior in the Earth. So this is long-term observation of in situ seismic velocities and attenuation in a cave. So essentially what this is, I've drawn a little diagram of what they're doing here because the figure was a little bit hard to read. Essentially what it is you have a cave with two branches to it. The person here shows that this is the inside of the cave, and then they have a source and they have a receiver. And so what they're doing is measuring the travel time across the rock here. And the strain is caused actually in this case by ocean tides. This site is right on the ocean, and so it experiences strains due to ocean tidal loading. And these are their results. And what I'm going to show you here is sea level. You can see is on the top, and EXX, EXY, and then this is the aerial strain, the EXX plus EYY. So this is the horizontal strain, the aerial strain. And a positive is extension and negative is compressional. And then down here, where you have the differential travel times that observed between this, with those waves traveling between two branches of the cave, and then we have the relative peak height is down here. So, but the part I want you to focus on is this one here. I've kind of drawn some lines on top of it to show you that there's some asymmetry here. So for the actual aerial strain, the peak-to-peak amplitude gets bigger and smaller, and it's bigger during new moons, during new moon and full moon, and it's smaller during the first quarter and third quarter. And but the peak-to-peak amplitude doesn't actually change that much, but you can see that it's asymmetric in that if you were to take the mean is not, the mean of the running mean of this curve is not constant. And so there's some asymmetry here. And if you look at that another way, if we look at the areal strain on the horizontal axis and the differential travel time on the vertical axis, we can see that when you're looking at the top of those of the curve, so we're looking at the when we're in extension up here at the top, those are these circles up here, they're proportional to the areal strain. So when you have a higher areal strain, meaning it's more expanded, then the differential travel time is proportional to that. There's some sort of a linear looking relationship between these two. But on the bottom part of that curve, so when you're down here on the compression side, there is no relationship between the areal strain and the differential travel time. It's faster, the differential travel times are shorter, so it's always faster when it's compressed, but it doesn't matter what the areal strain is. It's always about the same. And so the way that they interpret it is something like this. Essentially, I'll draw your attention to the right-hand axis here. Essentially, what they say is that when the strain rate is higher, the crack closure rate is lower. And so the strain rate is you can almost think of this as the peak-to-peak amplitude, because the period is essentially always the same. And so the rate and the peak-to-peak amplitude go with each other in terms of magnitude. And so they talk about this as having some kind of rate dependence. And if you think about it in these terms, it is a rate dependence, but I'm not sure that that's the right way to think about it. And I'm going to tell you how I think about this. I draw some other lines on this. It's the same curves. This is the areal strain and differential travel time. These two top axes and two bottom axes are exactly the same things. I've just drawn something different on them. And what I see is that the travel times are shorter when rocks are compressed than when they're extended. That's obvious. Okay, but the rock is softer when the peak-to-peak amplitude of strain is higher. That's slow dynamics. And the process of stiffening is slower than the 12-hour dominant period of the strain cycle. So what I've done here on the left-hand side is I've taken a constant strain value in red, and then I've gone down here and to look at what the travel times are at this constant strain value near the peak, so near the extension side of the cycle. And then I've moved those, I've marked those spots, and then I moved it down, copied it down here so we can see it better. And I've done the same thing, but kind of on the compressional side of the cycle. So the strain value is the same, but the travel times are different. So the travel times are always slower when the peak-to-peak amplitude is higher, both at the top of the cycle and at the bottom of the cycle. And that's why I think that the process of stiffening is slower than the 12-hour dominant cycle, because it gets slower instantaneously, but it takes some time for it to get faster as it's compressing. So this is more of a time-dependent process, more of a relaxation process than a rate-dependent process. So relaxation rate during extension is fast, but the relaxation rate during contraction is slow. So the period of the strain of oscillation is constant, and the peak-to-peak amplitude and travel time is nearly constant. So that's the travel time zone here. The peak-to-peak amplitude doesn't change much. So the peak-to-peak amplitude and travel time is primarily determined by the relaxation rate, not the strain rate. So that's how I interpret it. What the authors are saying is kind of similar, but I find it a lot more confusing. So if we look at this in terms of a time-dependent process, we can describe it as creep. So in the middle, I'm showing this curve that's showing a material driven to failure. So we have on the bottom, we have the creep time. So you have a material that's being loaded uniaxially to failure. You have this primary deformation part of it where cracks are closing if they're oriented with SH max, or forming if they're perpendicular. Then you have this slower crack growth, and then later on the cracks interact and join and the material fails. If you look at that in terms of what it may look like on some hypothetical plane, we would have, if SH max is in this direction, we would have cracks opening perpendicular to that, and we'd have shearing in a particular direction. If SH max was the other way, we'd have cracks closing. So that's the primary deformation, and that's really where we're going to be most of the time in the Earth, unless we're actually dealing with failure during an earthquake. Now, if we look at this in terms of the tidal stress and the tectonic stress, so the tectonic stress is usually in terms of megapascals. It's anisotropic and it's constant over the time periods that we're interested in. The tidal stress is more on kilopascal scale. It's almost isotropic. It's a little bit greater along an axis pointing at the place on the Earth closest to the moon or the sun by about a factor of 2, but that's latitude dependent. And it also alternates between compressive and extensional. So we have to take these into account when we think about how the Earth might respond under these kinds of pump probe conditions. So, for cracks that open perpendicular to SH max, the tectonic stress field will always try to keep them open. And for cracks that open parallel to SH max, the tectonic stress field will always try to keep them closed. So in response to tidal compression, these cracks will creep or close faster. So we would expect this process to be faster than this process because of the combination of the tidal stress and the tectonic stress. And so we have the peak-to-peak amplitude, and the travel time is primarily determined by the relaxation rate, not the strain amplitude. And when we measure changes in peak-to-peak amplitude and travel time, we are really measuring changes in relaxation rate. And so the relaxation rate is faster in the direction of SH max because the differential stress field is helping, not hindering the relaxation process. So the pump probe method in the Earth then is we measure differences in travel times in the coda portion of empirical Green's functions. One Green's function is calculated from the extensional periods and the other is calculated from the compressional periods. So you can think about it schematically like this. We have tidal forcing. That's a low frequency pump. That's about 12-hour period. And we have a high frequency probe. And in the case of empirical Green's functions, a period of about 5 seconds. And so we divide time into periods when the Earth is extended. So periods of time when we're above this horizontal line here. So this is the tidal cycle. So we take only these periods of time up here, beginning on the red vertical lines and ending in the blue vertical lines. And those are the extensional cycles. And then we do the same for the compressional cycles. And we calculate an empirical Green's function for both of those time periods. And then we compare the two to see how they, whether one is faster than the other. And we can also do this to the strain rate. So if we instead of looking at the tidal strain, we can do the tidal strain rate and get different parts of the strain cycle that way. So we can observe the stress-induced anisotropy. So if we measure the velocity when the Earth is in compression relative to what is an extension, the fractional velocity change is greatest in the direction of SH max because relaxation is faster. And by using different subarrays, we can detect small regional differences in the stress field. So this is a study in Oklahoma where on the left-hand side here, these are seismic stations, and I'm using different subarrays. So the circles that are filled in are stations that I'm using for to make the calculations immediately to the right. And the stress indicators are here. They come from the world stress map. And what I'm measuring now is the difference in velocities between when the Earth is in compression versus extension. And we expect it to be the largest amplitude, in this case, the largest negative amplitude in the direction of SH max, because relaxation is faster in this direction. And so as we saw way back in that cave study, we saw that relaxation was faster during the extensional part of the, we saw relaxation, that the relaxation rate was what was the limiting factor, not the strain magnitude. I hope that makes sense. I hope I didn't confuse everybody with that explanation. So this is how we measure the stress field, by measuring the anisotropy and the relaxation rates, is essentially what we're doing here. And we can see by using different subarrays, we can measure slightly different orientations of the anisotropy, and it matches pretty well with the different subarrays here. We can detect subtle changes in the stress field. So the other study that I'm going to talk about today is on the San Andreas Fault. And this is we often use linear elastic measurements to infer material damage or other properties related to damage, such as permeability and pore pressure. However, nonlinear elastic parameters are much more sensitive to material damage than attenuation or a linear elasticity. And we can see this over here. This is from this paper where they were looking at a sample that was damaged to failure and measuring changes in the linear elasticity in terms of the travel time of a P wave, the attenuation in the form of Q, and also the linear elastic parameter alpha, which is measuring the hysteretic behavior. And so if we look at this equation, this is what we're looking at. If we have a linear material, we have alpha equals 0, beta equals 0. We would expect that behavior like this. So the modulus is insensitive to strain. If we have alpha not 0, then we have hysteretic behavior. If we have beta not 0, then we have a slope. And then if we have both not 0, then we have the full kind of hysteretic behavior that we have seen in other materials in laboratory samples that I'm going to show you a little bit later. So again, using the same methods, we select periods of time of negative, neutral, and positive strain. So this time, instead of using just the positive and negative, we're doing positive, neutral, and negative for both the strain and the strain rate to get actually 6 different measurements. And then we calculate separate EGFs for each of the 6 bins. Then we measure travel time differences for 5-second waves between the different empirical Green's functions and use the differences to constrain the nonlinear elastic behavior. And I also look at this over different paths to try to get a spatial distribution of the behavior. So this is along the San Andreas Fault. The vertices of these lines here are where the stations are. So I have exterior paths, which is going to be sampling the Earth somewhat away from the fault. We're talking about kilometers away from the fault, a few kilometers. The crossing paths, all paths, and interior paths. So in that order, we're going from sensing primarily material away from the fault. This is sort of an average, a little more of an average, but moving closer to the fault and then moving only near the fault. And this is what the different behavior looks like. In general, we see that velocities are slower when the Earth is in extension versus when the Earth is in compression. The velocity difference between the 2 cases increases with decreasing distance to the fault. And for all but interior paths, the Earth is faster when compressing. That's the rate versus when expanding. for the interior paths, the Earth is faster when expanding versus when it's compressing. So what I've done is in the axes up here, I put the stars where I'm actually making the measurements, and then the hysteresis curves I've drawn as possible behavior that's consistent with the measurements that I've made. And so essentially what we can see here is that we can detect increasing material damage with decreasing distance to the fault. Both beta and alpha must be non-zero, and by improving the time resolution, we'll be better to constrain the magnitudes of the nonlinear coefficients. So I'm going to compare this to some laboratory studies. And so what I'm showing you on the right is behavior for different rocks, sandstones mostly, and then a granite at the bottom. And the axes are essentially the same thing. I've drawn them the same way so that we can compare them. And we can see that the behavior in the laboratory rocks is a bit more complex than what I've drawn, mostly because, of course, they have much better time resolution than I have, and I can't infer that kind of complexity with the measurements I'm making. But I ultimately, my results look pretty similar to the blue granite, especially the interior paths. So if you look at this hysteretic behavior where looking at both the strain rate and the strain, this is what looks like the blue granite is kind of the interior path with the single crossing loop. So that's the best comparison I can make with the laboratory study. There's also an in situ study here that was done with a vibro-sized truck. So this is the picture of the truck, and then here's a schematic of the experiment down below. There's a high frequency source, and then there's these two accelerometers down here. So we're measuring essentially the same thing. There's a pump and a probe. This is the pump, this is the probe. And so we're measuring the elasticity in situ over the course of the pump cycle. And this is what the results look like. It's in the same axes of what I'm showing you in my results. And in this case, the results look a bit like the crossing paths or the all paths, so a little bit further away from the fault. So the results here don't look like the fault core. They look a little bit more like what it looks like a little bit away from the San Andreas fault. So those are a couple of comparisons I can make. And it would take probably some additional laboratory studies in improving the resolution of the work that I'm doing to try to understand what we can actually learn in terms of things like pore pressure, permeability, earthquake cycle, that kind of stuff. Right now, just focused on making good measurements and doing the same thing that we're doing in the laboratory. And then the next step is to try to understand what we may be able to learn about the earthquake cycle and about things like pore pressure and permeability. And so that's the end of the pump probe part of it, but I did want to talk briefly about some seismicity and how that may be related to some of this nonlinear behavior in the Earth. And what I'm talking about here is that nonlinear affects earthquakes as well. And I have a couple of different studies that I wanted to show real quick. I know that I think I'm sitting at about, let's see, about 45 minutes. So I probably have 10 minutes for this maybe. I'm looking at the geysers here. This is in Northern California. I have a couple different earthquake catalogs that I'm going to show you, and also looking at Oklahoma. And the geysers is I'm going to call it a dry system. And the reason why I call it a dry system is because the water table is well below where the earthquakes are. So the earthquakes related to this geothermal system occur within the upper 3 to 4 kilometers, and the water table is at least 4 kilometers deep. They have to inject water. It turns to steam, and then it's extracted to generate power. but there is no liquid water in the system. Whereas in Oklahoma is a wet system. Of course, we know that they've been injecting, the oil and gas industry has been injecting wastewater into the Arbuckle Formation for decades, and there's been a lot of induced seismicity related to that. And so this is a system where we know that it's saturated in places, and it's a fluid-driven system rather than a steam system. And so what I'm doing is I'm looking at what the correlation between earthquakes and earth tides. And the way that I'm going to show this is I'm going to show this in terms of a likelihood function. And so what I do is I have two different cumulative distribution functions. So I have one on the horizontal axis here, time versus strain. So what it is that it's a cumulative distribution function of the amount of time spent at each strain level. So this is normalized between 0 and 1. If you are at 0.5, sitting here in 0.5, that means half of the time was spent half the time was at a lower strain level and half the time was at a higher strain level. And then on the vertical axis, we have a CDF of earthquakes versus strain. So if you're at 0.5, then you have half of the earthquakes happening you have earthquakes happening on the lower half, below the median strain and above the median strain. And if I plot these against each other, if there's no relationship between earthquakes and strain, then we expect a straight line between 0, 0, and 1, 1. And what I've done to make this a little bit easier to see is I've removed the slope, and then I've vertically exaggerated it. So the right-hand axis is exactly the same as the left-hand axis, except I've removed the slope and I've vertically exaggerated it. And I've done 100 realizations of a Poisson catalog, and those are in the blue, and then I've averaged them, and that's the yellow. And what you can see is that it's very close to a horizontal line, which is what we expect. That means that there's no relationship between the tidal strain and the occurrence of earthquakes. So in a Poisson catalog, that's what we would expect. I didn't put any. This is a synthetic catalog, and I didn't put any tidal component into it. So what I've done is I've done some other synthetic catalogs. I've done a non-homogeneous Poisson catalog with 20% tidal forcing. That means that the tidal forcing is 20% of the background rate, and it looks like this. That's on the left-hand side. You can see that now the curve goes below. That means that down here, there's a deficit of earthquakes at lower tidal strains. That's because more of them are at higher tidal strains. I can do it at 30%, and it's even bigger. And I can even make it proportional to strain squared, and it gets skewed to one side. So we can see here that in the case where I know that there's tidal forcing because I put it into these synthetic earthquakes, I know what it looks like. It goes like this. It goes below because there's a deficit of earthquakes at lower strains. If it was above instead of below, then there'd be sorry, I'm hitting some keys that I'm not intending to hit. If this curve went up instead of down, there'd be a surplus of earthquakes at lower strains. So what about aftershocks? So in a real earthquake, we have aftershocks and perhaps other kind of dependent events. And we want to make sure that other kinds of dependent events or other kinds of clustering are not going to masquerade as tidal triggering. I don't decluster my catalogs because aftershocks themselves could be tidally triggered or correlated with tides. And so if I decluster, then I'm going to remove my signal. If I'm looking for clustering, I don't want to decluster. So I leave the aftershocks in there, but I also check to see if aftershocks can look like tidally triggered earthquakes even when they're not. So what I've done is I've taken a real earthquake catalog at the geysers that has aftershocks in it, and then I've done permutations of it. And what that means is that I take 1% of the number of earthquakes, and I segment the catalog by that many segments, segmenting it by the biggest inter-event times. And then I take those segments and I randomly reorder them. So I'm preserving all of the aftershock sequences, but I'm just putting them in different places. And when I do that, I get this as a result. So essentially, what happens is that it doesn't look like it's tidally triggered, even though it has aftershocks in it. And so I could talk about this a little bit more in the discussion part of it, but I don't think, for various reasons, that aftershocks are going to masquerade as tidally triggered earthquakes. And so when I look at the geysers, I find there's tidal triggering, which is 18% of the background rate. If I look at the deep earthquakes, it's 17%, and the shallow earthquakes, it's 27%, possibly skewed here. And at Oklahoma, it's 60%. So this is just done by eye. So what I'm looking at here is that the red curve is the actual catalog. The blue are simulations, and the yellow is just the average of all the simulations of a Poisson catalog with different levels of tidal forcing. So the one that matches the geysers for all of the earthquakes is 18% tidal forcing. The one that measures the deep earthquakes, which is greater than the median, which is, I think, approximately, the median was it's in 2 kilometers. I'll have to look that up. But and then for the shallow earthquakes, it was 27%. So the shallow ones are more triggered than the deep ones. In Oklahoma, it's much bigger. It's 60%. And so this is just kind of a summary of those results. I did a binomial test as well, and I also tested it using this likelihood function, and find that the tidal correlation strength is 18% at the geysers, 60% at Oklahoma, and the binomial tests confirm that. And the other part of it is that the reason why I told you at the beginning that it's a wet and dry system is that at the geysers, it's correlated with the tidal normal stress, and in the Oklahoma, it's correlated with the tidal shear stress. And the reason I believe for that is because in Oklahoma, because you have higher pore pressures, you have a pore elastic response, which essentially cancels out the tidal stress in terms of its effect on Coulomb stress. And so the shear stress is driving the system, whereas at the geysers, we have a dry system, and the normal stress is driving that system. So I realized that was really quick. We can talk about it a little bit more in the discussion, but that's all I have planned for my presentation. And I'd be happy to talk about all this stuff for as long as people want to hang around.
Thank you. I'll invite everybody to unmute, long enough to say hello. Thank you for a fabulous talk. Really interesting.